Hello students, welcome to the class. In the last class we started with laws of motion, right? So in laws of motion already we have discussed about what is motion, what is the cause for motion. So what is the cause for motion? That is force applied on a body is the cause for the motion, right? So in the causes we discussed, that is, what do you mean by force? So force is nothing but what? Push or pull on a body is called as force. What all the effect will occur on a body due to the application of force? This we discussed. Types of forces we have seen. And after that, force of friction and Galileo's experiment, principle of superposition, then inertia of the body. The main concept what we discussed in the last class, that is inertia of the body. So in inertia of the body, we have three types of inertia of the body, that is inertia of rest, inertia of motion, inertia of direction. So inertia of rest, we have seen the example. So this is nothing but what? Due to the rest, the tendency of a body to oppose the change when it is at rest. That is called as what? Inertia of rest. Here we have seen the examples, and inertia of motion. This is due to the motion, the tendency of a body to oppose the changes when it is in motion. That is called as inertia of motion. So we discussed the example. Inertia of direction. Here the tendency of a body to oppose any change in its direction of motion is known as inertia of direction. So here also we discussed about the examples, and we saw that inertia and mass relation. Inertia is nothing but what? It is the measure of mass itself. Inertia is nothing but it is the measure of mass. Here, larger is the mass, more is the inertia. Lesser is the mass, less inertia. And the main topic, that is Newton's laws, in that we discussed the first law of motion. So in Newton's first law of motion, what it states, it is also called as law of inertia. So Newton's laws of motion, the first law states that an object continues to be in the state of rest unless and until any external force applied on a body. Suppose any force acts on a body, the body will move in the same direction of the applied force. Right? So this is Newton's first law. Example for Newton's first law. Right? In the last class, I told you to remember, that is, all the three laws of motion are also called as, the first law is called as law of inertia, second law is called as law of acceleration, and the third law is called as law of interaction. Correct? See here. So today we are going to discuss the second law and the third law, right? So before going to discuss the second law, here we need to understand one term called as momentum. Okay, because our second law is based on this momentum concept. Therefore, we need to understand first what is momentum of a body. See here, students, this momentum of a body, here mathematically how we can define. Here you can see it is already written here. Okay. This momentum is denoted by, how force we denote it by F, and acceleration is denoted by A. Velocity is by V. Similarly, the momentum is denoted by the letter P here. So mathematically, we can define this momentum of a body as, momentum is the product of mass and velocity. The product of mass and velocity of the body. Here you can see it is there. Okay, here it is written also. That is P is equal to M into V. P is equal to M into V. So the product of mass and velocity is known as what? Momentum of the body. So here you may ask me, What is the physical meaning? Okay, so this is mathematical. It is written the product of mass and velocity is nothing but what? It will give one quantity. So that quantity is called as momentum of a body. Okay. See, as we know that if you take any object on this earth, every object will be having some mass. So this mass, I'll take it as m. So when any force is applied on a body, what happens? The body will start moving, right? So when the body will start moving, it will acquire some velocity. As you know, the velocities are denoted by, the initial velocity is denoted by u and the final velocity is denoted by v here. Okay, so here what happens whenever this mass, all the bodies are having mass and its velocity, whatever it is. So the product if you take, it will give some physical quantity. So that quantity is nothing but what? Momentum of a body here. That quantity is nothing but momentum of a body, right? Here we can study different cases. We can see here it is written, that is, if a body is at rest, so what happens, students, when the bodies are at rest? Means here what I told, if the body is having mass m and moving with velocity u or v, here the product is m into v. Now what I am saying, the velocity becoming zero, the velocity value is becoming zero. So here m into zero, what happens? The momentum p is equal to, so m into 0 is nothing but what? 0 here, right? If the body is at rest, if the body is at rest, its velocity is 0. So its momentum is also what? 0. Its momentum is also 0, right? Second condition. So second point, that is the SI unit of momentum. See students, how to write the SI units? Already in units and dimensions you might be discussed. See, what is the formula? That is P is equal to m into V. Here you can see that mass is expressed in terms of kg, that is kilogram, and velocity is expressed in terms of meter per second. So the unit of the momentum is kg meter per second. We can read it as kg meter per second. Okay, we can see some examples here. If a truck is moving at very low speed, it can kill a person standing in its path because of the heavy mass of the truck, right? So here why this accident happens, when here what they are saying, here because of, that is, when a truck is at a very low speed. So even though the truck is at very low speed, due to its heavy mass, here the person will die. This is also because of what? Momentum. This is also because of momentum. You can see that is in the given expression. Here if you see that the momentum P is directly proportional to mass, and this momentum is also proportional to velocity, which means that if the mass of the body is more, the momentum will be more. If the velocity is also more, the momentum will be more here. So we can say that the momentum is directly proportional to mass and it is directly proportional to the velocity. See, next point, a bullet of small mass when fired from a gun, it can kill a person because of the large velocity of the bullet, here, right? So the impact of a body, it depends upon its mass and velocity. So what we can conclude here, so whatever the effect is occurring on a body, it is because of both, that is mass and velocity, right? So if any one value is more, either it is mass or it is velocity, the momentum will be more, correct? So this is what, this is momentum concept. Next we can see how we have the graph, the nature of the graph, that is momentum versus mass. See here, what is the nature of the graph here, students? Here the momentum and the mass graph is, it is a straight line. I hope you can see this, that is, it is a straight line. Why it is a straight line? Which what it indicates, as we know, whenever any graph is there which is a straight line or passing through the origin, we can say that these x and y axis quantities are proportional to each other. That is, mass and momentum are proportional to each other. So this is what graph between momentum and mass when velocity is kept constant. Okay, next you can see momentum and velocity graph. See, what is the nature again here? Again, the nature is a straight line, right? Again, it is a straight line, which means that again they are proportional to each other. See, it is a graph between a momentum and velocity when mass is kept constant. Okay, if this Newton, that is momentum concept, is clear, let us go for Newton's second law of motion. So what is Newton's second law of motion here? What it states, what is the statement, what is the example, and how we can prove this? See, the rate of change of momentum of an object is proportional to the applied force. It is proportional to the applied force in the direction of force. Okay. Here, the rate of change of momentum of an object is proportional to what? Applied force in the direction of the force. So understanding the statement is very, very important. So if statement is clear to you, then derivation will be clear to you. Okay. What they are saying, the rate of change of momentum. So slowly we can see this statement and we can write it. The rate of change of momentum means what? Here what they are saying, change in momentum. Okay. So here I'll show you the explanation part. Okay, students, here rate. Here whenever we specify the rate of change, here whenever we specify the rate of change, which means that the quantity is changing with respect to what? Time. This we should remember always. Whenever we say the rate of change, which means that the quantity is changing with respect to time here. So what is changing with respect to time? That is, the momentum is changing. That too, what they are saying here, see, they are saying change of momentum. So change of momentum. I told you already, the momentum is denoted by the letter P. Okay, suppose the initial momentum is P1 and the final momentum is P2, then change in momentum. How we take change in momentum? Change in momentum, we write it as P2 minus P1. So change in momentum is written as P2 minus P1. This is what change in momentum. So with respect to what it is changing, with respect to time it is changing. So this change, that is P2 minus P1, I can write it as, so this change I can write it as dP. So what is this dP here? So this dP, or sometimes we write it as delta P also. So this dP or delta P, it indicates that it is change. Change in what? It is change in momentum. Okay, it is change in momentum here. Right? That is, the change is denoted by delta P or dP. Okay. So this change is now with respect to what? Is with respect to time, right? So now, next part of the statement, the rate of change of momentum of an object, it is proportional to the applied force. So what they are saying, whatever the change of momentum is there, that is your dP by dt is there, it is proportional to what? Force applied. It is proportional to force applied in the direction of force. So that is dP by dt is proportional to F. This is the statement and its meaning. The rate of change of momentum is directly proportional to the applied force in the direction of the force. In the direction of the force, in the sense, for example, suppose here one body is placed. If you apply force in this direction, the body will move in the same direction. If you are applying in this direction force, the body will move in this direction. which means that here whatever the force you are applying in that direction, your body will move. This is what Newton's second law of motion and its statement, right? So mathematically we can prove that. Mathematically we can prove it now, right? So this only arrive at the point that is F is equal to m into A. See, mathematical formulation of second law of motion. If an object of mass m is moving along a straight line. So what they are saying, if a mass m is moving along a straight line with initial velocity u and is accelerated to velocity v in time t by applying a force F, then, so here according to the statement, the body is having mass m, initial velocity u and the final velocity is v. Here it is getting accelerated with acceleration of a, that also we can take. So according to all these considerations, we can write the initial momentum of the body. You can see in the slide, the initial momentum of the body is written as P1 is equal to m into u. P1 is equal to m into u here, where as we know, the momentum is given by the product of mass and velocity. The product of mass and velocity is written as initial momentum here. So initial momentum, initial velocity, therefore it is mu. Then next, final momentum. Why we are writing initial momentum and final momentum here? Because we need to take change in momentum. Therefore, we are writing it as mu and final momentum as mv. Then the change in momentum is written as P2 minus P1 is equal to mv minus mu is equal to. See, change I told you already. Change is nothing but what? Final minus initial. So in the previous chapter, you come across change in velocity. So how we write change in velocity? That is final velocity minus initial velocity will give the change in velocity. Change in velocity. Here change in momentum. Therefore, final momentum minus initial momentum. That is mv minus mu, which is equal to m into bracket v minus u. Here m is common, therefore I can take it out. Therefore it becomes m into bracket v minus u. Then rate of change of momentum. So this is important here, students. That is rate here momentum. What we got? Change of momentum. Here change of momentum. I have written it as m into bracket. This step, okay. M into bracket v minus u. Similarly, the rate of change of momentum. This is change of momentum. I told you already, rate of change means what? It is divided by time t. Correct? Therefore, m into bracket v minus u divided by t. So, or now, according to the statement, this change in momentum is directly proportional to what? Force. You can see here it is written like F is proportional to. So this step, F is proportional to m into v minus u divided by t. Now, as we know in physics, whenever we are using any proportionality sign, we can remove this proportionality sign and take equal sign. That is by taking some proportionality constant. Here the proportionality constant is k. Okay, there is F is equal to k into bracket m into bracket v minus u divided by t, where k is called as proportionality constant. But here, students, what is change in velocity? The rate of change of velocity is called as, in the last chapter we have seen, the rate of change of velocity is called as acceleration A. Here, change in velocity is nothing but final velocity minus initial velocity divided by time. So the rate of change of velocity is equal to what? Acceleration A. Therefore, here v minus u divided by t is equal to A it is. Okay, so in this previous step, that is F is equal to K into bracket, sorry, Km into bracket V minus U This is whole divided by t. So it is in multiplication. So whatever this part is there, that is v minus u divided by t, the rate of change of momentum, we can write it as k m into a. What is this a? A is nothing but what? Rate of change of velocity. So therefore, we come across the point that is f is equal to k into m into a. Okay, as I told you, this k is proportionality constant. So we are taking the value of k is equal to 1. Right? So k is equal to 1. Therefore, it becomes f is equal to m into a. This is Newton's second law. F is equal to ma. Now, what is the SI unit of this force here? The mass is expressed in terms of kg. Acceleration is expressed in terms of meter per second square. Therefore, the final unit is either it is kg meter per second square, or this kg meter per second square is also taken as Newton. So this Newton is denoted by the symbol capital N. You can see in the last line it is written. Everything is written. Okay. So this is regarding the Newton's second law statement, Newton's second law proof. So I told you in the beginning only, what is this Newton's second law is called as? It is called as law of acceleration. So why it is called as law of acceleration? You can see here, students, it is coming across the point that is F is equal to m into a. So till now we used to define the force as that is what we define, push or pull on a body is called as force. So this is physical meaning, or here we can also define the force as it is the product of mass and acceleration. The new definition for force, we can take it as the product of mass and acceleration. So don't get confused. Product of mass and velocity is momentum. The product of mass and acceleration is force. Okay, the unit is Newton. Yes, this is the final expression. Now let us see some examples for Newton's second law of motion. So the first example is a cricket player lowers his hand while catching the ball. You can see this picture. So a cricket man, what he is doing while catching the ball, he will lower his hand. I hope you might have experienced, you might have seen this. Okay, so why when catching the ball we people lower our hand? Not even only in cricket, you can take a throw ball also, right? So whenever you are catching a ball which is coming from certain distance, you will lower your hand. So why? Automatically it takes place. Okay, purposely we don't do it, automatically it takes place. You might have experienced this one, correct, students? So what is the reason here? This also we can explain with the help of physics law, that is Newton's second law. See, the explanation is when a person falls, because in the beginning only I told you regarding momentum concept. See, when a person falls on, see, that is F is equal to dp divided by dt. When a player lowers his hand, the time to stop the ball is increased. So what happens as you take your hands down, little down, here the time of that ball to reach your hand, the time will increase. So in the expression, you can see what is that? F is equal to dp by dt. In the denominator here, see, I'll tell you. That is, our expression is what it is? dp divided by dt. dp divided by dt is equal to force. This is our Newton's second law statement. What they are saying, when you lower your hand, the time will increase. The time will increase. Little increase to reach your hand. Hence, less force to be applied to cause the same change in momentum of the ball. So what happens? Because of the little more time, the force impact. See here, you can see that time and force are inversely proportional. Correct? So when they are inversely proportional, if the time is increasing, the force will be less. The force will be less. That is dp by dt is equal to F. Here dt is more, which means that the force will be more. Therefore, when the force will be more, the change in momentum of the ball is also less. Sorry, time is more, therefore force is less. Therefore, to avoid this damage, here what happens? Suppose if the force impact is more, what will happen? It may cause damage to our hand. To reduce the force on our hand, what we are doing? We are increasing the time duration. So when you increase the time duration by taking your hand lower, here what happens? The impact will be less. You might have experienced this one. So next time what you can do, you can practically do it. So while catching the ball, you just take the hands down and down. You just observe what will happen. Okay. This is what first example. So why we take our hands down while playing a cricket. Okay. Next, this is the example. Next example is a person falling on a cemented floor gets injured, but a person falling on a heap of sand is not injured. See, from the same height. So you just stand on one cement floor and you just stand on a heap of sand. Okay. So if you fall from the same height on both, here on cement floor, the impact will be more than the heap of sand. Means on cement floor, you will get hurt. On heap of sand, you will not get hurt. Why? Again here, Newton's second law explanation. See, when a person falls on cemented floor, the rate of change of momentum is very large. What they are saying, the rate of momentum is very large because the person is stopped in a very small interval of time. Okay, when a person falls on cemented floor, the rate of change of momentum is what? Very large. Here, because of that reason, the time interval will be more, hence he gets injured. So what they are saying here, see, already I told you mass depends on what? Momentum depends on what? Mass and velocity. So here, the mass of that cemented floor will be more than this one, that is heap of sand, correct? Then after that, here, whatever the time interval to fall on the cemented floor will be less than the heap of sand, right? So because of that reason, what happens? Here the person will get injured when he falls on the cemented floor than the heap of sand. So see the second paragraph, when a person falls on a heap of sand, the change in momentum takes place. The change in momentum takes place in longer interval of time. As we know, if the time interval is more, then here the force will be less. The impact will be less, therefore he will not get injured. Okay. So after the example, we can go for the Newton's third law of motion. So what is Newton's third law of motion states? Okay, so Newton's second law we have seen, Newton's third law. So why this picture is inserted here? This is one example for Newton's third law of motion, right? Here you can see a person is kicking a football. How this is example for Newton's third law, we can see in the definition part. See, you can take it as the explanation of that figure, and you can also understand the definition of Newton's third law of motion. So what is the statement? Statement or example, that is when a body A exerts some force on another body B, the body B also exerts some force on body A. So vice versa, that is if if a body A is exerting some force on the other body B, the body B also exerts some force on the body A. So this is nothing but, we can understand one example here. Here, when an apple is falling from the tree, that is A. So it is coming towards the earth, that is B. Okay. Here, what is the meaning of this first line? When apple is falling from the tree, the apple is attracted by the earth. Similarly, the earth will also get attracted by the apple. But you may ask me, when apple is falling down, why there is no movement in the earth? Here what happens, students, the mass concept will come. Okay, compared to the apple mass, the earth mass will be more. So because of that reason, no doubt it will get attracted, but we don't feel any difference because of the large mass difference. So that is only Newton's third law here. When a body A exerts force on B, the B also exerts some force on A. When a player kicks a football, the football moves forward and the foot moves backward. So this was there in that picture. So when a player kicks a football, not only a football, you can take whenever you kick a ball, here what happens, the ball will move in the forward direction. You might have experienced this also. Your foot moves in the backward direction. So this is also because of third law of motion, that is action and reaction. Next point, the force with which the football is kicked is action. Here, third law of motion is nothing but what? It is a pair, action and reaction. It is a pair of action and reaction. Okay. So when you kick a football, it will move in the forward direction. This is what? Action. Due to this action, the football moves forward. Similarly, see, the football will also exert some force on your leg. So that is what? Reaction here. The force exerted by the football is what? Called as reaction. So action is, you are kicking a football, it is moving in the forward direction. Now, the football will exert some force on you or on your leg. This is reaction. Due to that, your foot moves in the backward direction. Therefore, this third law of motion is called as what? Law of interaction. Here, interaction between the two bodies takes place. Am I right? Therefore, it is called as law of interaction. Okay. So, action and reaction pair is there. So, one is action. Due to that, the changes will occur. Other is reaction. Due to that, also the change will occur. See here. Action and reaction on different masses. Always you remember that action and reaction will be on different bodies it takes place. It is not on the same body. Action will be, you can understand the example of football kicking. Action is on the football, reaction is on your leg. So this is what action and reactions are on a different masses. See, earth is pulled up by the whatever the stone we have taken. Similarly, the stone will also exert force on the earth. So here we have the statement for Newton's third law of motion. Okay. The statement is, to every action, there is an equal and opposite reaction. So for every action, there is equal and opposite reaction. Why it is equal? The force will be equal for both, but they are in the opposite direction. So this is the statement of Newton's third law. To every action, there is an equal and opposite reaction. So with the help of two spring balances, which is interlocked together, this can be proved. That is, action and reaction are on the two different bodies. Here you can see the figure. Okay. So when you interlock two springs, when you apply the force, here what happens? You are stretching it. You are stretching the one spring is attached to the rigid support and the other spring is set free. So when you stretch it, when you stretch it, here what happens? Action is on the second spring and the reaction will be on the first spring. So this is action and reaction on two different bodies. So the springs are interlocked to each other is the example. You can see here one more example. When a bullet is fired from a gun, it exerts a forward force on the bullet. Correct, the bullet moves in the forward direction. So this is forward force. This is nothing but what? Action. And the bullet exerts an equal and opposite force on the gun and the gun recoils. So this is what? Reaction. So action and reaction here you can see. The for bullet, when you trigger this gun, here what happens? The bullet moves in the forward direction is action. In the same way, the force is exerted on the gun, therefore the gun recoils. So this is also example for Newton's third law, that is action and reaction pair. Next, when a sailor jumps out of a boat, he exerts a backward force of the boat and the boat exerts an equal and opposite force on the sailor. This is reaction and the sailor jumps forward. See students, how much the physics is impacting our day-to-day activities. So here, in that is walking is also because of this action and reaction pair. So here what happens? When a sailor jumps from a boat, the boat will apply some force. Because of that reason, he will move forward. So he will also apply some force on the boat. Therefore, that boat will push little backward. So this is action and reaction example. So here one more example, that is what the figure is. Rocket launching. See, the reaction of a rocket is an application of the third law of motion. Various fuels are burnt in the engine, which produces the hot gases here. So when the rockets we are launching, you might have seen this one in the movies and in TVs, right? That is when it is, that is, if you are launching the rocket, here what happens? We are burning the large amount of fuel. When the large amount of fuel is burnt in the engine, what happens? It will produce some gas. So gas will move in the downward direction. The hot gases push against the inside tube of the rocket and escape out of the bottom of the tube, right? So the hot gas is coming out of it, that is action. Reaction is what? Due to that force, due to that pressure, the rocket pushes in the upward direction. As the gases move downward, the rocket moves in the opposite direction. So this is third law of motion. Example, right? The rocket launching is also example for third law. Next, so that is swimming. You might be knowing swimming is also example for Newton's third law of motion. How here students? A swimmer pushes the water backward with his hands. This is what? Action. So this is what? Action. So when suppose if you are swimming, you might be observed or experienced this. So what you will be doing? You will be pushing the water in the backward direction with the help of your hand. This is action. So the reaction is what? Your body will move in the forward direction. That is reaction. The reaction offered by the water to the swimmer pushes him in the forward direction. So whatever the force is acting on you due to this is making you to move in the forward direction. So this is what swimming example. Okay. So just now I explained you motion of rockets is also due to the third law of motion. conservation of momentum. So our next concept is, so this complete all the three laws of Newton. First law is called as law of inertia, the second law is called as law of acceleration, and the third law is called as law of interaction. So here, conservation of momentum. This is statement for conservation of momentum. The statement is, here you can see the figure, its explanation and the statement. The sum of momenta of two objects before collision is equal to the sum of momenta after collision, which is provided there is no unbalanced forces acting on them. Here see students why they have specified, that is unbalanced force, because we know that if the balanced force is acting on a body, the body will not change its position, right? It will be at rest only. So unbalanced force in the sense, here what happens when unbalanced force is acting, the body will change its position, right? So that is unbalanced force will change the position of the body here. So law of conservation of momentum is, in absence of this unbalanced force, means no force is acting, then this valid, the statement is valid. Means the momentum before collision is equal to momentum after collision. So see the explanation part so that the definition or the statement will be clear to you. In short, what we can say, if the momentum before collision and the momentum after collision both are same, then what we can say, the total momentum is conserved. The total momentum is conserved here. See here, that is first figure. First two balls, you just observe it. That is having the mass m(a) and m(b). So we can say that consider two balls of masses m(a) and m(b), or we can say it like consider two balls A and B having masses ma and mb moving with a velocity ua and ub. Okay, here what is happening, the force is exerted by the ball. Okay, if two balls A and B having the masses traveling in a straight line with initial velocity. So as I told you, when any object is there, it should move with some velocity. So the velocity of these two bodies are taken as UA and UB. For A body it is taken as UA, for B body it is taken as UB. And if here this is very, very important, UA is greater than UB. What is the meaning here? The initial momentum of body A must be greater than the initial momentum of the body, sorry, velocity of the body B is more. The two balls will collide with each other. So when the velocity of A is more than the velocity of B, automatically what happens? The A will come and collide with the B. So because of this collision, so when two bodies are hitting each other, we call it as collision. So during collision at a time t, ball A exerts a force FAB on ball B, and the ball B exerts a force FBA on ball A. Means here the force exerted by A on B is given by FAB, and on B and A is given by BA. See here, A exerts a force FAB on B and B exerts a force on A, that is FBA. Okay. Now, when the two bodies will collide, the two balls will collide, the velocities will change. Initially, it was moving with initial velocities UA and UB. Now, the velocity will change. The velocity will change to VA and VB. Here, this is what the final velocity of the bodies after collision. The momentum of ball A before and after collision is written as. See, understanding this is important to understand the derivation. Okay, the momentum of A is given by what? MA UA. This is for what? Before collision, because before collision the velocity is UA. and after collision the velocity changes to VA. Therefore, it is written as after collision the momentum of A body becomes MAVA. Similarly, for B body, before collision it is MBUB, and after collision it is MBVB. Understanding? For A body, what we have done now, for A body, I have taken initial momentum and final momentum. Similarly, for body B, I have taken initial momentum and final momentum. Now, so the change in momentum for the ball A during this collision is given by, that is MAVA minus MAUA. This is what the change in momentum. So always change is what? Final momentum minus initial momentum. Okay. You can see here, students, the final momentum is MAVA for ball A minus initial momentum for ball A is what? MAUA. Now, here, what I can do? So this step is little changed here. Okay. Changed in the sense just alignment. Okay. See, next step, what it is? The rate of change of momentum of ball is given by. So this for ball A I am writing, okay, for ball A, the rate of change of momentum. I told you already, change in momentum in the previous step. Here you have seen change in momentum is given by what? MAVA minus MAUA. So one more step we can increase here. What is common in both? MA is common. Therefore, it is VA minus UA. Am I right? Now, the rate of change of momentum. As I told you, rate of change of momentum means what? The change in momentum is changing with respect to what? With respect to time. That is MA, I have taken it out. MA into bracket VA minus UA, sorry, VA minus UA. This is UA, okay? Divided by T. Similarly, for ball B also we can write. So for ball B, same way what we can write, MB into bracket VB minus UB whole divided by time. This is what I have written. The rate of change of momentum for body A and for body B separately I have taken. Now see how the Newton's third law is applicable here. See the next paragraph. According to Newton's third law of motion, the force exerted by ball A on ball B is equal. So whatever the force is acting, no doubt the A ball is having more velocity than the B ball, but whatever the force is exerting by A on B and B on A, it is same. It is same, but in the opposite direction. Therefore, what we can write, you can see this step here. You can see here, that is FAB is equal to minus FBA. I told you already what is FAB. The force exerted by A on B is FAB. Next, force exerted by B on A is FBA. As they are in opposite direction, the minus sign will come. Okay, what is FAB? FAB is nothing but what just now we have seen. The rate of change of momentum is proportional to force applied. Therefore, we can write it as MA into bracket. So here it will change. That is, here I'll write this. Little the alignment is changed. So what is FAB? FAB is what? Rate of change of A body. That is MA into bracket VA minus UA divided by T is equal to minus into bracket. Why? It is in the opposite direction. MB into bracket VB minus UB divided by T. So students, here time we can cancel it and we can simplify the equation. So we can multiply this to the bracket. It becomes MA VA minus MA UA is equal to minus MB VB minus, minus into minus, it is plus MB UB. Now the simple thing what we are doing here, this minus sign one side and the plus sign one side we can take, or we can also rearrange it as the initial velocity terms one side, the final velocity term one side, the readjustment. So what I'll do, I'll write, that is initial momentum terms one side and final momentum terms one side. See, this VA is what? Final momentum of A body. Now initial final momentum of B body, what it is, here you can see, that is minus MB into VB. It is minus, so if I take it on the other side of the right equal sign, it becomes plus MB VB. This is equal to, so this MB UB I'll write as it is. So this minus MA is written, taken this side. So minus, if it comes to the other side, it becomes plus. So it becomes plus MA. So now here you can see, students, one side you can see here red equation, this one. It is written with the red ink. You can see this. The initial momentum terms are one side for body A and B, and the final momentum terms are one side on body B, A and B. Therefore, MAUA is what here? See this one. This MAUA is what? Initial momentum of A. Next, MBUB is what? Initial momentum of B. So plus is there, which means the sum of momentum before collision is equal to MAVA, final momentum of A, MBVB, sorry, initial final momentum of B body. That is sum of final momentum. The statement is what we saw the statement here. See, our statement is what? The sum of momentum of two bodies before collision is equal to the sum of momentum of two bodies after collision. So here we have seen that only. So this is the proof of what? Newton's that is conservation of momentum. So Newton's second law proof we have seen, and we have seen the conservation of momentum. So we can discuss the sums directly or the tricky one based on this. So you should remember the final equation. MAUA plus MBUB is equal to MAVA plus MBVB. So this is conservation of momentum. So students, in the today's class we have seen what is momentum, what all the factors which is affecting momentum, that is mass and velocity, how it is affecting by the graph we have seen, whether it is directly or inversely proportional. After understanding the momentum concept, we have seen that second law of motion. So second law of motion will give you the equation force is equal to mass into acceleration. Then third law, its example. Then the last point is conservation of momentum. Okay. Then in the next class, we can see the further concepts. Okay, students, thank you.